Hello and welcome to the Open Systems Media panel discussion, Scaling IoT Applications. I'm Kurt Schwader, your moderator, with today's speakers, Mark Wright from AILA, Aido Ose from Intel, Stephen Graves from Object, James Kirkland from Red Hat, and Stan Schneider from RTI. Today's schedule consists of about 50 minutes of panel discussion, leaving 10 minutes at the end of the hour for audience Q&A. Before we begin, let's run down some important features of your viewing console. First is an enlarge slides button. This button will maximize the slides to fill your entire screen. The download slides button allows you to download and print the slides if you'd like a hard copy to follow along with. The button labeled forward to a friend enables you to send an email to someone that will include a registration link to this eCast so they can also attend. The Ask a Question text box enables you to participate in today's event. You can simply type your question into the box and submit it using the Submit button. You can submit questions at any time during the material. We encourage you to do so early and often while you're looking at it and the question is fresh in your mind. We'll address as many of these as we can during the closing Q&A, and if you have a question pertaining to the eCast operation itself, you can submit those too, and one of our technicians will be happy to respond to you during the eCast. This and all Open Systems Media eCasts are copyrighted and may not be recorded or used in any way without the express written consent of Open Systems Media. We have an all-star lineup of panelists today. Mark Wright is the Director of Partnerships and Evangelization at AILA Networks. He has a long and successful track record in military, industrial, and consumer markets prior to entering the IoT space. His background in high-reliability industries and familiarity with products and technologies like embedded internet and Wi-Fi makes him a valuable asset to the IoT space. Aido Ose is the Director of Business Development and Marketing for Intel's IoT Group in the Quark Solutions Division. Aido has been involved with a number of IoT vertical business applications ranging from startups and global enterprise and brings a depth of IoT experience to the panel. Stephen Graves is the President and CEO and co-founder of Object. Stephen has persistent storage expertise and embedded database expert as well. Stephen complements his skills with a far-reaching background in embedded and real-time systems programming as applied to IoT. James Kirkland is Chief Architect for the Internet of Things and Intelligent Systems at Red Hat. James has a depth of experience in Linux and Unix and has significant experience with IoT solutions in transportation and energy sectors. Stan Schneider is the CEO of RTI, the Industrial Internet of Things connectivity platform company. Stan is an industry pioneer and visionary within the IoT space and has vast experience in applications and use cases. He's also a member of the Industrial Internet Consortium Steering Committee. Welcome, gentlemen, and thank you very much for participating in today's panel. Let's get right to it. We're going to do something a little bit different than most of our IoT panels today. We're going to do a top-down approach, and let's start with the big picture real-world examples. Provide an example of an IoT environment where scaling was a challenge, and what application and what were the scaling factors. How was the IoT system architected in order to scale in those dimensions, and what kinds of scaling strategies are employed to meet these requirements? Let's start with Stan in RTI.
Hi, I'm Stan Schneider from RTI, and first of all, I want to push back a little bit on the term IoT. It's become too big. It means too many things. At least like to divide it into two pieces, the consumer IoT and the industrial IoT. Just to be clear, RTI is very focused on the industrial IoT. Consumer IoT is mostly little devices with relatively simple connections into the cloud or something like Fitbits. The industrial IoT is more about new infrastructure for transportation, healthcare, energy systems, everything like that. We're very much more in that vein, and I can't put a Fitbit or a little wearable health device like that in the same breadth or category as what I'm going to talk about, which is GE Healthcare's LCS division. It's one of the biggest healthcare companies out there. I actually did a webinar with them last December, I suppose, with their chief engineer, and asked him in the webinar how many products he manages, and he didn't know. They have many, many products, ventilators, respirators, oximeters, incubators, and on and on and on, all the things you see in a hospital today. In a lot of industrial Internet of Things architectures, those are all independent devices built by independent teams. They do a sales channel. Other than that, and they sell to the same kinds of people. Other than that, they're pretty independent. But the future needs to change, and needs to change drastically for two reasons. The biggest one, actually, is that today's hospitals have a problem they don't like to talk about. The Institute of Medicine put out a report last year that said that the third leading cause of death in the United States after cancer, heart disease and cancer, is actually errors made in hospitals, and most of those errors are made because the processes, while they're very careful with everything, there's just so many things going on, and it's all completely manual. And by building an intelligent distributed system that can monitor what's going on between these types of devices, you can get around the alarm fatigue. That's a big problem. You can be much more intelligent about when patients are really in trouble. You can do things like make sure you've got the ventilator on or the cardiopulmonary bypass machine on. But today those things aren't even connected to each other. They don't even know they're connected to the same patient. It's really needs to change, and this kind of a stressor is across it's really a microcosm of the industrial Internet of Things. Same kinds of problems in autonomous cars, surgical robots, the smart grid, the smart city, where you need to add intelligence and build a large distributed system at the same time. Anyhow, GE's big problem is finding patient information, connecting the very complex data types between these devices, running throughput issues across the system. There's many different types of devices, many types of networks. There's wired, there's wireless, there's mobile device interfaces, and the kinds of issues they run into are module interface control, because now you have to have many different interacting modules, different types of products, operating systems change over time. Will my network be able to perform, give me the latency I need at the throughput levels they have? How do I even understand what the data types are and the data models between these systems, avoiding the trap of putting your data type, coding it hard-coded into your application code. And then, how do you find the right data? I want to track Stan Schneider around the hospital. He's a patient. 61% of patients move every day in the hospital. And it's really a big problem with that. You can't just send all the data to everybody. So, the architecture, which I will talk about more later, is the data centricity is the key to that architecture. Interact with a common data model, not with each other applications. And, critically makes your application much simpler. It scales much better. It allows multicast interface control and subsystem isolation and redundancy and all those kinds of things that make large systems reliable and really work. I had to choose this from a lot of different applications. We have something like 1,000 applications out there. It's not the largest one, but it has a lot of great characteristics that I can talk about later.
Okay, great. Thanks a lot, Stan. James.
Excellent, thank you. So, when you look at IoT problems and you begin to try to solve them, some of the challenges that you run into around scalability and their sisters, manageability and security, they can be very abstract. It's really important that, at least from our perspective, that you don't design a solution for any particular problem in just in the lab. You've got to go out and you've got to test to scale. You've got to make sure that a solution that works in the lab or works in a small locality or in a small some portion of a system is going to scale out. So we've worked with customers in transportation and energy, for example, that have both in the two examples I'm thinking of, that they had a solution in both cases that they tested either in a small a small area geographically, and the system worked fine, but it never worked at scale. And then they ran into problems managing it when you get up into the tens of thousands and hundreds of thousands of devices. So that's really the first half of it. The second half, and this, really goes to the heart of it is the key to IoT is getting the data to the right place to make the right decision at the right time, and then to take that data and gather it all together to get long-term insight, and do that in a way that's safe and secure. So, we work, for example, in the rail industry with the entire North American freight rail industry to work on positive train control, which is a security system, but gathering all that data from signals and from locomotives also gives you the ability to gain insight into problems like predictive maintenance and fuel efficiency, things like that. When you look at one North American railroad, they found that if they could increase their average fleet speed by 1 mile an hour a year, so essentially, the average miles per hour of the entire fleet over the year by 1 mile an hour, it was more than $200 million in essentially reduce costs, which goes right to the bottom line. So, there's a huge financial impact, and you need to pick your projects carefully, and you need to test them in the right manner, and really know what the desired result is that you're trying to get to.
Okay, great. Thanks. Steve, your take on the big picture?
Yeah, thanks, Kurt. So as a vendor of a software stack component, specifically a high-performance database management system, we're not directly involved in building production IoT systems. So citing one or more specific examples, then the challenges faced and conquered is kind of difficult. But we work closely with our customers that do build such systems, such as building automation systems, factory automation, and like James just talked about with Red Hat train systems. So a database system for the Internet of Things, whether it's going to be on a device, on a gateway, or in the cloud, needs the ability to scale out and scale up. So an example of scale out means, for example, adding more sensors to a gateway. So the database system on the gateway needs to be able to maintain performance when it's receiving input streams from 10, 50, or 500 sensors. A primary consideration in this case is concurrency. In other words, the ability to insert data simultaneously from multiple threads without those threads blocking each other. So pay attention to the database system strategy for providing concurrency. Is it a pessimistic model? In other words, one that involves proactively locking things in the database, or is it an optimistic model? Optimistic meaning without locks. So if it's a pessimistic model, then is it database locking? Is it table locking? Is it row locking, or some other level of locking? The amount of concurrency that you can expect is going to be directly correlated to the locking granularity. For an optimistic strategy, in other words, when there's no locking, then you need to think about the number of conflicts that are possible. In other words, two threads trying to modify the same thing at the same time, and the conflict resolution strategy. Another example of scale out is increasing the number of gateways. So if the gateways are feeding a cloud, then the cloud stack, including the database system in that stack, needs to be able to accommodate the growing number of gateways. If there is no cloud and the gateways have remote access capability, in other words, the individual gateway databases are each a shard in a database in a cluster that's supported by the database system, then the distributed database solution needs to be able to support the anticipated scale out. In practical terms, that means being able to scale from a distributed cluster of 10, 50, or 150 gateways. In the case where the gateways feed a central cloud, the approaches are going to differ based on whether immediate consistency is required or eventual consistency is tolerable. And for most cloud systems, eventual consistency is going to be just fine. Now, scale up means the ability to store increasing volumes of data and maintain performance. In other words, when the database size grows from 10 megabytes to 100 megabytes, which you might see on a gateway, or 10 terabytes to 100 terabytes, or even petabytes, which would be more typical of a cloud, then consistent database performance is important even as the database size increases, and you're going to want to avoid using hard disk drives in favor of solid-state technology in order to eliminate what we call rotational latency. That's the time it takes to wait for the platter to rotate and the time for the disk head to slew back and forth. And rotational latency becomes exaggerated as the database occupies more space on the physical media. So, obviously solid-state technology doesn't have any of those moving parts and completely eliminates rotational latency. So if you can go to solid-state technology and eliminate rotational latency, then one of the biggest challenges is going to be the depth of your index trees. Each level of a B tree equates to a logical I/O, and I/O is costly for any database system, regardless of the storage used, including in-memory databases. Two strategies to minimize that problem are going to be use a different type of index, for example, a hash index, and sharding the database. A hash index is not a tree that grows deeper, so the performance remains constant. And with respect to sharding, a single logical database can be broken into, for example, 5 shards. So each of those shards' index tree only holds 20% of the total, and therefore it keeps the depth of the B tree and the associated I/O cost to a minimum.
Okay, great. Thanks, Steve. Aido, your thoughts on the big picture?
Absolutely. Yeah. From an Intel perspective, obviously, huge company that's focused from an IoT perspective on almost every use case you can think of, from retail to industrial to transportation, smart cities, home, a lot of consumer use cases, as well as ADAS and autonomous driving. So just a ton of things that we're focused on. I'll probably just share one example of the way in which Intel is really focused on helping to drive standards. Really, I think the key to scalability is really a coalescence around open standards so that we can drive scalability as well as helping to accelerate time to market for our customers. So from a pure silicon perspective, I think Steve made the point earlier, which was a great point, that this is really about distributed systems and how distributed systems become intelligent. So when we think about being able to scale from a Quark processor to a Xeon processor in the cloud and having the appropriate middleware and firmware in place to support manageability of these end nodes as they make their way through the network, I think it's really important that from an Intel perspective that we really drive forward those standards and bring together an ecosystem of partners that are adopting and building shared architectures from an IoT perspective. Here in San Diego, where I'm based, there was a port project a year ago that was really focused on leveraging the San Diego port, which manages about 35 miles of shoreline here in the San Diego Bay. And the goal was to better manage energy consumption and reduce greenhouse gases. And the focus was to take an ecosystem approach where we leveraged ISVs, system integrators, obviously technology provider. Intel provided the IoT gateway. And the goal was to monitor HVAC usage, chilling towers, utility meters. There were a number of different systems that were loosely connected via SCADA systems. But the intent was to get a more normalized view of the data, to get a more granular data stream in terms of timeliness and latency, and to pull that into a visualization system that would make actions more real-time and more appropriate for the management. Our belief as it relates to the scalability of small projects like this really kind of have to do with the ecosystem of partners that I just outlined and really kind of leveraging a myriad of different technologies to pull together kind of a best-of-breed approach as it relates to both unlicensed and licensed band technologies, whether they're mesh architectures, star topologies, or what have you, and really pulling together kind of the technology infrastructure that's required to meet the security and manageability requirements of a specific use case and vertical. I'll talk a little bit more about that as we progress.
Okay, great, thanks. Mark, you're next. Big picture.
Very good, thank you. So Ayla is a platform for manufacturers of things, right? So primarily consumer focused because it's a time to market. We improve the time to market play. So in general, though, for this question, if not handled in a planned manner, all IoT fieldings can be a challenge, right? So because IoT adds communications, it adds cloud, it adds app as additional development steps to a device manufacturer's development process, right? So 3 additional things that need to be considered. And then on top of that, what needs to also be considered is the experience that the customer will go through, right? So you have to also look at that customer experience. So organizationally, this becomes an application test and QA problem as part of the overall engineering problem as well. So if the decision to build versus buy on the cloud is favored toward the build, then that needs to be tested, right? So the spooling up of how will the infrastructure manage in terms of scaling up. If a platform is decided upon, then the platform manufacturer can, of course, spool up enormous numbers for short periods of time to test capacity, to test transient scaling, right? So that part is risk mitigated. So that's what this becomes. It becomes how do you mitigate the risk, particularly when there's additional development stages being put onto a product manufacturer, right? So we also need to consider those scaling as it applies to the customer experience, right? How do all the features interact? What are the features of this product? What are they going to be? But how do they also interact? Because various people will use them in ways that you may not even have thought of. So, another example could be device middleware that's incorporated into that device. HomeKit, Alexa, how do these things perform with your own UI, right? Is there a language problem? That can affect the experience of your users. What about so IoT provides a great platform for managing your product when it's out in the field, when it's in the customer's hand. How do those PM features work at scale? Example, if you're doing OTA, if you're doing over-the-air updates to update that product, whether it's for security, whether it's for new features, how does that happen over different time zones, right? How do you manage that so that it's a seamless effort to your users? Then we've got the issue of the gateways, right? If your product requires a gateway because from internet to the wireless, you've chosen a protocol that's either lower power than Wi-Fi or much more nodes or much higher range. Now you have to look at what's that ecosystem. Are you allowing other manufacturers to tie in? Then you also, when you scale up, how do you ensure that all those products work together, right? So what you want to do is have this tested beforehand in your various development stages so that when you do go out, you have favorable press, right? Because unfavorable press immediately becomes a brand problem. So, one of the customers that we work with, Owlet, if you look there in January of 16, Engadget wrote an article where they have 6 billion heartbeats in over 6 continents. So this is a product that goes on an infant and helps monitor, their health. The Fast Company in June 9th said, Outlet product has saved 20 babies in 9 months. So that's the kind of press you want.
Very good. Yeah, lots of great information there on the big picture. We're talking about everything from applications at the high level down to kinds of things that you're going to be dealing with locking and scalability with, down to the persistent storage. On to the next slide, please. We're on topic 2 slide now. Let's talk about prototyping. So in today's agile world, we have a natural approach, which is basically to take your environment products or what have you, bootstrap your IoT application, storyboard it, and then prototype it to prove out the use case. Now, once you're through with the proof of concept, what are the important scaling requirements that need to be considered, and how do you measure them in the prototype environment? In terms of increasing in sensors, number of users increasing, geographic reach, performance, all those kinds of things. How do you establish proper scaling metrics when you're prototyping in this kind of environment? Aido?
Yeah, I'll take that. One of the things that we take advantage of is our tremendous ecosystem around our ODMs and Intel Labs as an example. So we have a number of different in-house vehicles that we use to do prototyping and to actually do proof of concepts. Some of these are funded projects, co-funded projects, and from an IoT perspective, it's really important to make sure that you're not only solving a technical problem. From my perspective, you're really solving a business problem, and there needs to be a positive, scalable, robust business case. behind what you're doing, and to make sure that the support model behind the approach that's being prototyped is something that could scale, right? So some of the scalability requirements have to do with business model. Some of them have to do with the technology and the architecture. And then there's also support model considerations as well. So some of the building blocks we look to leverage are beyond the silicon, and they have to do with software. And so, some of the expertise that's come over as part of the Wind River suite and number of platforms that are deployed in various verticals are really key in helping us really understand, device manageability. What's the provisioning process? If you're talking about in-node sensors or gateways, how do you manage the firmware and the security from sensor to cloud, and really making sure that if you have a need in your use case to run analytics at the edge and to be really smart about what data you're taking into the cloud, that you have a way of managing that code and making sure that you're delivering what I call a frictionless experience for the developers that are going to take you these tools and actually develop applications from them. So, from our perspective, as many of the gentlemen have already outlined, there are a number of different ways to solve a problem from an IoT perspective. I think if you're relying on open standards and technologies like 6LoWPAN, or if you're going to do a mesh implementation, if you can do something that's open as opposed to proprietary as much as possible, I think these are going to be some of the key things that we look at to make sure that you've got longevity for whatever solution you put into place. Lastly, when you talk about the geographic challenges, I think that's one of the most pernicious problems to cover when you're kind of in a lab prototyping environment. So it does help to have partners that you can work with to understand some of the local requirements, both whether it's what band is supported. If you're talking about some type of sub-G type of implementation, what bands are supported in a particular geography. And there could be local regulations that are also sometimes missed until the end. So those are some of the things that I'd highlight.
Okay, great, thanks. James?
Yeah, and those were excellent points. I mean, I think that, first you have to make sure that everything has been highlighted several times, that you're building on a base of open standards. And then from that, you're going to have an information model that models out, the device types that you're going to have across the entire environment, what type of information or data they're going to be producing, and then the flow of that data through the system. And then you're going to have to take that, and you may in your labs have some of these. You will have some of these sensors in real life that you can manipulate, but you also need to have a harness that's going to be able to probably cross geography simulate these devices and a large number of them to do scale testing, and to do failover testing and high availability testing and things like that. So you really need to know what normal data and abnormal data is going to look like, and then you're going to need to have both gateways and sensors that you're simulating to test at scale. And I think it's really important to do that. The other thing you're going to need to do is, once you have all that, you're going to need to go through and have a tree of failure scenarios that you're going to begin testing that are complex sets of failures, so that you can see essentially when you have simple failures, how that's going to be handled, but then complex series of failures as well. So not just having one device fail, but having multiple devices fail, or multiple devices go into error condition in different geographies or within a particular geography. So, it's not just coming up with an information model that allows you to look at, processing data in its normal state, but processing data in failure state, or when you're out of bounds, whether it's temperature data or whatever, how you're going to handle alerting that, whether you're going to shut down generators, shut down devices. So it's really simulating. And then the next would be simulating managing a large number of these devices, right? If you've got to push out a critical update, say there's an SSL vulnerability or an SSH vulnerability or something like that, how are you going to, in a decent amount of time, be able to push out to 50,000 devices or 100,000 devices a fix? If they're all over very low bandwidth connections, if that takes 2 months to do, there's a pretty wide vulnerability window.
Okay, great. Stephen.
Yep, thanks, Kurt. I think James just made some really excellent points. I think a team should ask themselves or also consider what's the anticipated scale-out need, and then what does that imply with respect to processing power, connectivity, and the number of tiers that you're going to need in your IoT system. In other words, do you have devices and gateways in the cloud, or do you have devices and gateways that feed another level of gateways that in turn feed the cloud, and so on? An IoT product or system could be pretty modest. For example, a network of sensors connected to a handful of gateways, connected to a single server for monitoring a nuclear power plant. Or it could be very large. For example, a network of wind power farms where each generator in a farm is feeding one or more local gateways that in turn feed regional servers in the cloud that are then aggregated into one holistic view, and everything in between. If an IoT system needs to control a real-time environment, then what does quote-unquote real-time mean? Does it mean controlling an actuator within 1 millisecond in response to an input? Now, how many things have to be controlled in whatever your definition of real-time is? And it's only by knowing that these details, you can begin to spec out the requirements for processing power, communication, bandwidth, and so on. Your prototype should be capable of simulating the real world so that you can know as empirically as possible how your IoT system needs to scale to meet those performance requirements. And I know someone is going to say this, and I think Stan already did actually in his opening remarks, that this is impossible at scale. And it is, but you can't just punt either. Further, an IoT system can be closed and well-defined, like the nuclear power plant example that I cited earlier, or it can be a loose association of data-generating devices and apps that can't be entirely anticipated in advance, which is probably more typical of home automation, where first there's a Nest thermostat, and then the home security system comes into the fold, and then the lighting system, and then garage door openers, and so on. So those two scenarios potentially call for different types of database systems. In the first example, where everything is well-defined, you'd benefit from a conventional schema-based database system, whereas in the second example, where you can't anticipate all these data-generating devices, you might benefit from an OSQL, in other words, a document or a key-value pair type database system that can more easily deal with new and or unstructured data. Schema-based database systems offer more, and in many cases, easier ways to manage the data because they're aware of the data structure. On the other hand, NoSQL database systems obviously don't need to know the structure of the data up front, so they're a bit easier to adapt to new types of data, especially data that's inherently unstructured.
Okay, great. Stan.
Hi. So I sort of missed what Stephen said. I said in the first thing, but that's okay. I'm going to give him a plug in a second anyway. I think the most important thing you need to realize is that there's many dimensions of scale. It's very confusing for people at the prototype stage because they're all interrelated. It's very hard to anticipate which dimensions are going to impact you in the future. We've done a lot of work on this. We actually have found that there's 3 dimensions. Since they're all correlated, there's 3 dimensions that seem to be relatively independent that you really should look at. And the first one I like to call performance at scale, which is really what latency you need at what throughput. Looking at latency without throughput is a primrose path to doom. I think you really need to understand that. But For instance, our hospital application I talked about before, they have, heart waveforms and video switching and some intelligent decisions to be made that can be, their latencies aren't nearly as critical as some of our systems like defense systems and robotic feedback and even in the medical space, CT scanners and things like that. But there's a lot of data. Some of it's time critical. You really need to understand performance at scale. The second one is a number of software modules that are going to be interacting. People leave that out. They don't think about it, but when you get to be a large system, especially a large distributed system, GE has 300 different types of products, you really need to have interface control between them. We have systems with 1,500 teams of programmers working together. It becomes a critical thing. And the last one is, I like to call addressable data items. It really is the issue. You can't send everything to everyone. If you can send everything to everyone, you don't have this problem, but systems get large, finding the right data, finding Stan Schneider's medical data in the hospitals or moving around, or, the right wind turbine phase variance, or which air traffic and which tracks are important for my air traffic control collision algorithm is really hard. So those three things, actually, all the other dimensions for a distributed system we found can be characterized in some way by those three things. So it's a fundamental decision, the same decision really as a database, because DDS, the standard, is like a moving database. And I will end very quickly saying, do not invent your own protocol. There's standards out there with thousands of use cases that really have been down the path of how to analyze these systems many, many times. They sound like they're all the same or confusing. They are not the same. I'll move on.
Okay, great. Thanks, Dan. That's right. So, Mark, your thoughts on prototyping and what angles need to be considered with scaling?
Sure. Thanks, Kurt. So I'm going to look at this section as what you're doing just prior to going into production, right? So you've done your proof of concept, you've done a few prototypes, you've come up with your MVP. Now, really, you want to be you want to be doing a number of pilots here before production, right? So it's really getting down to doing your test, iterate, and again, finding out what that customer experience is going to be, so you don't have truck rolls once the product is out in the field. So you have to consider, are you geographically spread out in terms of your product launch? Even if you're just in the U.S., right? There's just different time zones out there. If you're international, right, you want to test out your app naturalization, right? You want, for the features that you put in, you want to know the performance at the limits of your guaranteed capabilities, right? And how they're working, as mentioned in the first section, how they're working with each other. And as Stan mentioned, there is the latency part you want to look at. You want to look at the timing of the TLBs, right? What happens if a lot of things are happening very quickly, and what happens if the internet connections aren't so great where you're actually fielded, right? If you allow call groups, what happens when these are maxed out, right? So this can happen also in if you have RBAC, role-based access control. So what happens if you've got conflicts there? So IDO, it wasn't IDO, it was Steve mentioned, right? If you've got a pessimistic model or an optimistic model, how do you handle this if you've got role-based and conflicts come out? Because again, when you push this out there, people don't know how you expected it to behave. They know only how, the customer only knows how they expect it to behave. So you want to ensure all the components will work at the anticipated build-outs, right? You want to test your setups under different conditions to ensure that you're not going to run into problems when you're first fielding out.
Okay, great. Thanks a lot, Mark. We are now to the topic 3. So slide 3 is next, prototype to production. So now we're through the proof of concept. We've understood some things. Hopefully we've considered scaling. What kind of strategies can you now employ to scale for production? For example, as the sensors increase, the increased information transfer puts pressure on gateways, clouds, maybe the devices. What kind of strategies can be used to scale gateways, cloud applications as users increase? What kind of strategies are there to make sure that the number of users can scale without bringing down the IoT system? And then, how do we scale gateways for geographical reach? Let's start with Stephen.
Okay, thanks, Kurt. So I'll take the last of those. Scaling geographically can imply that a gateway is doing more than simply gathering data from sensors and then shipping it up to the cloud. In other words, if the data is being analyzed with the intent to control the actions of the things in this Internet of Things in more or less real time, then that analysis needs to occur as close to the edge as possible. It really isn't practical to send the data up to the cloud, do the analysis there, and then send control instructions back down. That's probably stating the obvious, but I'm famous for that. So the gateway should utilize the software stack components that can scale. So in the context of a database system, that means the ability to store more data while maintaining performance, handle increasing numbers of concurrent connections without creating bottlenecks, and being able to process analytics at the edge before shipping that data up to the cloud. And I covered a number of those things in my first remarks, so I won't repeat myself here. But even in the case where the cloud system is performing analytics for purposes other than real-time control, the cloud still might not need fine-grained edge data. Rather, pre-aggregated data spreads the analytics workload between the gateways and the cloud so that the cloud systems don't become overwhelmed. I'll give you an example. A gateway in a building automation system will want to control HVAC equipment in real time. As soon as the room temperature reaches the threshold, turn the heating off or turn the AC on. But in the cloud, we might only be interested in knowing how many hours per day the HVAC was on and how that compared to other days with similar weather patterns, which could be a leading indicator of a problem with the HVAC system, predictive maintenance type issues, or whether we're getting the anticipated return on investment from an HVAC upgrade. Now, an example where you would want the cloud to have granular data is train systems that we've talked about a couple of times for analysis after an incident. So manufacturers of locomotives have an interest in knowing if the conditions that led up to an incident were caused by human error or by faulty design, and you need that granular data for that type of analysis. But in either case, the ability for the software stack components to efficiently process analytics is obviously critical. So the lesson here is if you need to perform analytics at or near the edge in addition to at the server, and you want support for those analytics from the database system, which I think you do because, as someone just mentioned before, I think it was Stan, you don't want to reinvent the wheel, then that's going to narrow your database system choices. In other words, you want an edge database system that can also perform analytics and not just be a way station for data on its way to the cloud. And as Aido pointed out, the reusability of software from the edge to the cloud is advantageous.
Okay. Great. Mark, your thoughts on prototype production?
Okay, thank you, Kurt. So on this stage, I'm going to look that we're in production here, right? So doing the previous steps, we should already know how scaling will perform on our products as they're being bought because we're, over the top successful with our product that's out there. So now we're taking advantage of IoT, we're getting this data, and we're pushing that out to updates, right? So how do we handle the scaling of that? So a platform you use should have a developer service or a sandbox, as well as the production that you put out. And you should always have a number of products that you've got out on that developer service that you'll trial your changes, right? So you want to use the same baking type procedures that we talked about earlier when you're doing your POC, when you're doing your prototypes, but also when you're doing your pilots. You want to do that on your developer service so that you know how it's going to affect, right? There's nothing worse than having all of this success out there and then putting a change that's going to brick your products. And that's what you don't absolutely want, right? So again, it's a matter of test and iterate, even when you're in production, but now it's on this developer service, right? So whether it's gateways or products, you need to do this. But another thing, now that your products are in production, it'd be good to consider pushing them to know their limits, right? So something very similar to a HALT that's used in the semiconductor industry where you're doing accelerated life testing. So what you're aiming to do here is know the weak points of your system so that you can determine if it is of concern for your market or for your customers, and then you can determine the ROI. And something like a HALT or a HALT type mentality is very good because you're going out and you're pushing out this customer experience. And because it's a customer experience, people will use it very differently. And keep in mind, you've got these different components in there, not just a product, but the internet connectivity or the connectivity that you're using, the cloud, and then the app, right? So the app and the connectivity in the product is something that the customer will see. You also want to have contingencies for updates. This will be required. Example, if you've got an increase in security on HTTPS certificates, right, was increased from SHA-1 to SHA-256. What happens if your customers don't update? They keep saying no for the update, right? If they keep doing that, eventually they'll get to a point where it's bricked. So how do you anticipate and communicate to your customers, even with other techniques, that this is important and it needs to be done? So it's this type of it's knowing what can happen and then preparing for that, because as your volumes are growing, unforeseen circumstances can come about.
Okay, great. Thanks, Mark. Stan.
Hi, great. So first of all, I want to push back on the question again a little bit. Your question under says, how do you scale user devices in the industrial end of things? User devices aren't all that relevant. There's going to be 50 billion devices out there. Those are not user devices. They're devices doing things. So, the fundamental scaling and things that you find out in the field is, discovery. How do you find all the devices, find the data? Filtering, how do you send the data you need, and really it becomes a lot about robustness and redundancy, and it's much harder to recover from problems in the field. You need somebody on your team who has failed. How's that for a recommendation? We have actually taken down the entire train traffic on the East Coast because of our software. We have seen customers we worked for years on projects and fail. We've been thrown out of projects and then gotten back into them. We haven't failed one in a very long time because we have a lot of experience with this. The biggest problem you will not find your scale problems in the lab or development. We have a great lab. We have a test harness that can run thousands of applications and 10,000s of endpoints and realistic data sizes and rates, and we have hundreds of different types of machines that we can interoperate between. You probably don't have such a thing. I would suggest you find somebody that has some experience with that and make sure it works, because you absolutely need realistic testing. It's often really a challenge, but you can't rely only on that. Like I said, you need someone on your team that has infrastructure products that have been proven at the scale that you anticipate, and ideally even at the scale that you don't quite anticipate. Geographic scale is also challenging, and we're doing continent-wide air traffic control. Harmonic video switching is also continent-wide things. You missed also the sometimes there's an imperative also to scale down, not just up. We have a micro version of our product that run on very small devices. It's very important sometimes, especially challenging when you integrate very small devices into a larger system with large devices and powerful systems, and how do you delegate responsibilities and make sure it's compatible. So I think it's really important as you're going into production, that you've actually done a lot of the work up front in prototyping to make sure that you have some experience with systems of the magnitude that people are working on. The biggest change in the industrial end of things is most of these systems are for the first time really going through larger scales, larger integrations, more reliability requirements. It's vastly different than the consumer end of things for that and many other reasons. So.
Okay, great point. Scaling down as well as scaling up. We didn't touch on that one. Aido.
10 seconds.
Yeah, great set of comments from the speakers. Ultimately, you have to think about security, reliability, manageability. We've touched on these themes previously. I'd also like to throw in, for certain use cases, functional safety as being a key requirement that in some cases gets implemented on the silicon but has to be actually enacted as part of the overall application. We also think about the importance of ease of implementation of the solution. If you're going to develop an application that gets handed off to a system integrator to be implemented, in some cases that system integrator might be in other geographies, and you may not be geographically close to the application provider or the solution provider. It becomes really important that you've optimized the experience, the out-of-the-box experience, so that you can streamline implementation and support. I've seen deals killed because a great solution takes too long or is too complex to implement. So that's something that I think we need to keep in mind as well. I think there was a report out of the University of Michigan maybe a year or two ago about how students were able to take a laptop and go into the intelligent transportation system and start changing traffic lights and traffic signals. Very easy to hack into and some of those early proof points. So end-to-end security cannot be understated, and that kind of starts at kind of the endpoint device level and identifying ways in which you can protect devices and user identities, protecting the operational integrity of the device, allowing each device to basically, attest to its ability to join the network and authenticate. Obviously, there's network and cloud level, security that's required. Many of the gentlemen on this phone could speak more specifically to that. I know from an Intel perspective, the McAfee suite kind of gives you the ability to manage, threats and aggregate threat intelligence over multiple vectors so that you're able to benefit from, many implementations and threats that are hitting systems. And I think we'll see an increase of this, as IoT really achieves scale. There's various levels of firewalls and even within the gateway, the ability to manage integrity at the gateway and sensor level. So we continue to really harp on security because we think that ultimately is one of the weak links that, if not properly managed through standards and standard architectures and implementations, could really undo and great efforts, and to the point that was raised earlier, create a lot of bad press.
Right. Good points, Aido. Yeah, safety and threat vectors is a consideration. James. James, are you on mute?
Oh, sorry, I was talking to mute. Yeah, so I think that really one of the important things, we've talked about data and the data journey. When you look at this from a life cycle standpoint, especially with the devices and the broad infrastructure that you're going to have out there, moving from prototype to production really requires, especially with industrial use cases, requires you to have that infrastructure. We've talked about the gateway as a key point in the infrastructure in a lot of different ways. But you need to be able to have intelligence on that gateway that you're going to be able to quickly change as conditions change and as you get information flowing through the system. So that's why we recommend that you have an ESB, something that can implement enterprise integration patterns and a rules engine that allows you to have rules, and that both of these can be manipulated or changed outside of the core code, so that you can push behavior down into the gateways quickly without having to test all of your code, but only testing the changes in those engines themselves. That way you're able to make quick changes to how data is collected, aggregated, summarized, transformed, and then acted on at that gateway level, so that you're able to, as other people have said, push that intelligence out to the edge, but also control it in a fine-grained manner within, particular localities, within classes of devices, whatever it is, because you're going to have to, with these systems, make changes in relatively short fashion in a manageable way. You're going to have to test those those changes in reproducible fashion. So it's really important to have some analysis and control system that's on those gateways. That as another speaker alluded to, the gateways aren't that just comms gateways that are there to gather and route sensor traffic. They're there to intelligently make decisions about what data gets routed up to the cloud, what gets stored, and then also it's watching that data and taking action, whether that action's alerting, whether that action's shutting something down, whatever that is. You need that intelligence locally because there's the bandwidth restrictions, as we've talked about, the cost restrictions of cellular data, but there's also the need whenever you have an interruption in connectivity back to the cloud applications to be able to act autonomously in something close to a normal fashion.
Okay, great. Thank you so much. A lot of great points. We are now to the Q&A. Lots of great information and discussion on these topics from the panelists. We're time crunched, so we're going to have to do a lightning round here. I'm going to ask each panelist a question from the audience, and please try to keep your answer to 20 seconds or less so we can kind of get through this. Mark, there was a question about legacy and legacy systems. Is that a limitation in terms of being able to do something within the IoT environment? And how you might be able to transition legacy?
Yeah, so there's two ways on that. One is there are systems in place where really you put on a connectivity solution, and you can very easily transition a product that's already existing to an IoT product. You do have to do all the considerations we've discussed. And similarly, if you've got a legacy cloud system and that you're migrating, you can do a cloud to cloud and still incorporate those legacy products. So yes, it can be done.
Okay, great. I'm sure Layla has a lot of good information on that as well to contact them. James, lots of talk about open standards and open protocols. Can you comment on what standards and consortiums are tackling these kinds of things?
Well, I mean, you have a broad range. You have things like the Industrial Internet Consortium. You have folks like AllJoin and 1M2M and lots of different ones. And I think the mistake that people make is that they try to lock themselves into one standard. Red Hat's position all along with standards is that we're trying to support as many as possible because each use case is going to need something different, whether it's DDS for some use cases, MQTT for other use cases, REST or CoAP. You need to have a golf bag approach and be able to have all these different clubs in there, and you pick the right one for the right implementation.
Okay, great. Makes sense. Stan, there was a question about why not further segment IIoT into specific segments like services and maintenance, manufacturing, medical, and other.
First of all, I love that question. The best answers, because the whole point of the IoT is the power of a common architecture. You need to segment by requirements, not environment. Just like animals in biology, there's air, sea, and land animals, but you can't segment them by the environment and do anything architectural. A whale is not much like an octopus. They're both sea animals, but they're not like all. But architecturally, it's very much like a bear. Medical, transportation, energy are also environments. It's really not relevant. The industrial and things disruption is really exactly these common technologies coming through and sweeping away the industry-specific standards. You need an industry, IoT industry-wide, sensor to cloud, interoperate between vendors, scale, latency, reliability, redundancy. Those are the kind of architectural patterns and standards that satisfy the needs of the systems. It really is the big mindset change that industries need to make is get away from the industry segments except for data models and look at how you can leverage that. There's great work being done by the IIC. I'm on the steering committee in both the business strategy and architecture groups, journal papers, analysis tools, gamification approach, and very soon an update of the architectural work that's been done that includes standard recommendations.
Okay. Aido, is these IoT or IoT bottlenecks in terms of scalability, are they mostly hardware or software or a combination?
Yeah, I think you'll find a combination. Obviously, on the hardware side, you've got to make sure you pick the right hardware to handle the compute and performance needs of a specific use case. Obviously, firmware that sits on top of that hardware, whether it's RTOS-based or whether it's full OS, has to be optimized to meet performance requirements. But I think some of the bottlenecks are more related to manageability and security, which I think you'd find more on the software side. And then to go back to the question that was raised earlier, the Open Connectivity Foundation is one of the great ways in which I think multiple ecosystem players are coming together to kind of minimize some of the risk of software scalability.
Okay, great. Also pulled up the resources slide. If the audience is interested in that, the resources slide is now up. Stephen, there's a locking strategy question in terms of databases, and they're seeing some things about time series databases in the scaled IoT environments. What's your opinion of SQL versus scaled time series?
Yeah, so I'm gonna push back on both aspects of that question. SQL is available for time series databases. Our database, as an example, has time series capabilities, also offers an SQL API with built-in analytics. And the question also made the contention that simultaneous access isn't necessary for a time series database, and I disagree with that as well. You can have data being ingested into the time series database from sensors or whatever the source might be, as well as doing analytics on it at the same time. So you've got both read and write access going on at the same time. And I could give a more elaborate answer, and I probably will take it offline with the questioner. But bottom line is, it isn't. The locking strategies aren't unique to just traditional SQL databases. They apply across the spectrum.
Right. Okay, great. Thanks. We've run out of time for today. I want to thank our panelists for sharing their insights on scaling IoT. We at Open Systems Media, Ayla, Intel, McObject, Red Hat, and RTI thank you, the audience, for attending. You contributed excellent questions. I'm sure our panelists will get back to you on the ones we did not get to. This eCast will be posted online at the URL shown on your screen in 24 hours. Note that an audio-only podcast version will also be made available there, and Open Systems Media events are copyrighted and may not be recorded without the express written consent of Open Systems Media. Thanks for attending. Have a great day.